afternoon, jury and opponents. I'm Lucas of the Hong Kong team, and I'm reporting on problem 2, electrical damping. The task is a magnet is suspended by a spring, displays simple harmonic motion when it is in place. And if it operates within a coil connected to a resistor, then its motion will be damped. And so our task is to investigate the factors that affect the damping. So here's a quick task demonstration, and yeah, please get the case. So with an open circuit, we just have a harmonic oscillator that is damped by air resistance. And so this is the infinite resistance limit, and we'll add the electrical damping on top of this system. And here's a qualitative explanation. So qualitatively, the motion has a few distinct phases. At the very top, the magnet is momentarily at rest, and so there's no flux change to the coil, and so there's no voltage, no braking force. However, as the magnet starts to fall, it picks up some speed, and somewhere between the peak and the rest position, it will reach the flux for the coil will change fastest, and so this is where the induced voltage and braking force will reach the maximum. And then like at the center, then like the flux change goes to 0, and so that means that both the electric force and also the force just like go to 0. And past the center, like everything just happens with a flip polarities, but the force like still points upwards. And then on the return phase, like it's just the same. So here's the theoretical explanation. So first we model the base oscillator from the coil, as I mentioned, and so like the springs don't have actually non-negligible mass, so that's why we have to add like 1/3 of the mass of the total mass of the springs to the effective mass, and also the time and the spring constant. And so the first step is that we do not treat the magnet as a point dipole, and instead we treat it as a uniformly magnetized cylinder, which is equivalent to a sheet of anterior surface current. And so we just calculate the mutual flux between one magnet loop and one coil loop, and like it will give us this Henkel transformed expression over here. And then after we integrate over all four magnet loop pairs, then like this is how we obtain the closed form distribution of the flux. And like this is where the offset enters through a 0 order Delta function. Yeah. And step 2, like we need to find like the coupling constants for both the axial and radial components. And we do this by taking the spatial derivative. And like here are some key maps that show what this looks like. And then finally, like this is where the coupling comes in, and we just simply use this formula to calculate the BMF. And this is the final coupled ODE, like with accelerations over here and the circuit component over here. And so now I'll proceed to the experiment. So to test to make sure our theory is correct, we just use these base parameters, and we also like vary these 6 parameters independently, and also perform 3 trials to be able to compare bars. And our experimental setup is we use this dual spring design to minimize like off-axis motion, and we also like use like this release mechanism, which allows us to like release without any axial like any radial oscillations. And this is like how I vary the different parameters that I mentioned. And we also track the motion using April tag, which is a very accurate and proprietary like manual stuff. And then to calibrate the magnet spring, we use this Hall probe linear stage setup, and as you can see, like using the surface current model allows us to get a good fit. Yes, so preliminary experiment 1 is we just show the open circuit, and as you can see, there's no force because there's no induced current because like the circuit is open, and yeah, and so this is like however, with a closed circuit, you can see like the displacement will decay exponentially roughly, and like yeah, and you can see good theory experiment agreement. And when we also add like an axial offset, which is where we move the coil vertically relative to the magnet, we also observe this asymmetry because the magnet is more time in the top half of the coil versus the bottom half, and so that's how we get these phase diagram shapes. And because like it's not exactly an exponential curve, so that's why we have to like calculate the envelope for every single data point. Like we do not assume it's an exponential one, and we quantify the damping as like the half-life when the amplitude decays like half the original. And so external resistance is like a relatively intuitive one, and like it's really just a constant problem. And you can see that when the resistance goes up towards infinity, then it just reduces back to the base case with like the half-life determined entirely by air resistance. And also our theory allows us to predict the critical damping, but that requires a total resistance of like 1.7 ohms, and that's not really achievable with normal setups. So that's why we don't really show that here. And we also allow our theory also explains like the axial offset like more quantitatively instead of just the qualitative asymmetry. And you can see that there's actually this this minimum point which occurs when like it spends most time in like this maximum region of the coupling, and so that's also like why the minimum half-life, aka the maximum decay, occurs roughly around the coal edges. But like it's not exactly that, but like yeah, it's very accurate. And so the radial offset, like you can also see like it gives a very harmonic shape, and that's because the bezel function is like offsetting a lot. Yeah, and for the number of turns, they also varied it, and you can see good agreement. But the number of turns only enters really through the flux calculation, and so that's why it doesn't really affect the half-life that much. And we also vary the release position, and like this actually shows that like the half-life is the same for the equal amplitude. And that's just because like and this is because the decay is not really an exponential curve, and so that is why like if you change the release amplitude, actually the half-life will be different, and you can see like our theory actually manages to capture this, while like naively thinking exponential just like basically give everything a constant half-life. Furthermore, we also vary the strengths of the magnets by essentially stacking multiple magnets on top of each other in the holder of our experimental setup. And so and you can also observe great theory experimental improvements over here. And we also give a couple other further insights. And so firstly, like when we do a Fourier transform on the frequency of the displacement and the EMF data, that we may observe like some interesting spikes at like specific base frequencies, and we can explain this through like the coupling function from before, and like when the coupling function is like approximately odd over the oscillation interval, then if we assume the base oscillation is like roughly this, then it will just like kind of like keep it as an even oscillations. And then if it's an even function on the interval, then that will give us like roughly odd oscillations. Yeah, and so it's like the more specific derivation of how exactly like the Taylor expansion allows us to predict the higher harmonics. And as you can see, like when we actually run this for the experiment, then yes, we do see like spikes at even frequencies for the roughly odd function interval, and spikes at like mostly the odd frequencies for the even function interval. And yeah, and you can see like this voltage will have a frequency which is approximately double that of like the base spring oscillation frequency. And we also show a heat map of the like the relative strings with these dimensionless parameters. And like of course the heat map will change depending on like the different specific geometries, but like this is approximately what it looks like. And you can see that when the magnet like when the equilibrium for this magnet is centered on the edge of the coil, which is this dashed line, then like we will only really see like the odd frequencies. And for the displacement spring, like the frequency of the spring is like much stronger. Like the spring is like affecting the frequency much more than like the damping is. And so we just mainly see like a line over here at like the like the natural frequency of the system. And we also analyze exactly how the phase portraits change. So the phase portrait will produce a low if and only if like we have the velocity equal to 0 or the coupling is equal to 0. And so we'll only get like a second over here if the equilibrium position of the magnet is smaller than the amplitude. And if you plot like this invariant, then you can see like the number of lobes is approximately like conserved, and the area as well is can be predicted by our theory very well. Like our experiment is shown here on the crosses, and you can see it also allows us to predict the specific phase portrait. So in conclusion, what we did is we used the Empyrean loop model and solve a couple ODEs numerically, and also do not perform any zero order analyses. And furthermore, our experimental setup uses a dual spring cable tie system with an axial release mechanism, and we also verify like a wide range of different parameters. And we also get further insights regarding the higher harmonics and also the phase portrait shapes. So here are the references, and thank you for the presentation.
Okay, thank you so much. Okay, so it's a time for questions of the opponent. Go ahead, 2 minutes.
So did you model the self-inductance in your theoretical model?
Yeah.
I saw in your theoretical model, but did you consider this when computing when solving numerically?
Yeah, the numerical model is the full model.
Okay, thank you. And then did you, for your critical velocity calculations, did you assume constant damping?
Huh?
Did you assume a constant damping, like a linear damping when you modeled the critical velocity?
No.
No, you didn't. So, okay. And then for your 2 spring setup, were any of the springs ferromagnetic?
No.
Okay. And then for your do you have like any like parameterization of the coil where you say the number of turns, the inductance, the geometry, the wire layering, where you like define this so that we can see that this don't change during when you vary the parameters, for example. Okay, while you find it, can I ask one question? But how did you video track the small oscillations? Or how did you track the small oscillations?
Using automated able time.
And is this able to track like oscillations near the center, for example?
Yes, the camera is 4K.
Okay, I think. And then also, how long did you conduct your experiments for?
So the experiments conducted roughly around a minute, but like we may cut out like the later parts.
Why did you cut it out?
Because like otherwise it'd be very messy to the graphs.
Okay, thank you. And then, did you account for temperature decrease? Did you measure like if the temperature increases due to the for example, voltage induced?
The temperature wouldn't increase. Like it would, but it'd be so minuscule that like.
Did you verify this experiments?
You can verify the order of
Yes or
magnitude
no?
calculations.
Did you?
You can verify the order of magnitude calculations.
And then what integration method did you use?
Sorry?
What integration method did you use?
Integration method.
For solving your numerical model?
Well, we just compute numerically. We can use quadrature.
Sorry, what was it?
Quadrature.
Okay, thank you so much. It's time for you to prepare. Okay, the time is on, so go ahead with the presentation. You have 4 minutes.
So my name is Kirashna, and I'll be opposing on problem number 2, electrical damping. So firstly, I would like to start with the task, which explicitly states that we are to investigate relevant parameters. So that's what I will be focusing on for the majority of the proposition. So moving on to the presentation summary, we see that for the theory, he used a Hankel transformation to model the magnetic flux. He then he also modeled a coupled system where he considered the mechanical as well as electrical effects and how they affect oscillations of the magnets. Further on for the experiments, he used 2 non-ferromagnetic magnets, which is a very nice and stable way of controlling the z direction and ensuring that the magnet only oscillates in 1 dimension. And then we also see that the magnet, they also investigate oscillations where the magnet goes outside of the coil, which we do not think is relevant to this task. However, I will elaborate on this in the discussion points. They also, the parameters which they varied were the release amplitude, the stacked magnets, as well as the number of coil turns. And then they also video tracked using the APOTrax software. Further on the conclusions, we see that they investigated frequencies, they made phase maps, which present further insights. However, the parameter variations, which were the main task description, were only qualitatively compared with theory and experiments, and the phase portraits did not have any experimental data at all. So moving on to the points which we thought were fully fulfilled, they modeled a coupled system, which we think is very appropriate for this problem statements. They also account for the resistance of the coil, and they also map where the magnetization of the magnet is strongest and weakest. For example, the magnetization is strongest for the edge effects of the coil and weakest for the middle, which we thought was very nice qualitatively explained. And then they also modeled the inductance, which we think, again, is a very important part of this problem formulation, as the coil possesses a self-inductance. Furthermore, they also investigated regimes such as the critically damped regime, which was also nice to see. And then they also described the coil extensively with the radius, length, and number of coil windings. And moving on to the partially different points, they only have qualitative comparison of theory and experiments, which we would appreciate a quantitative theory to actually see the correlation. Furthermore, they primarily focused on the frequency investigation, which was not the main problem formulation task, and rather this time should have been spent to look at the parameter effects. Furthermore, they had a lot of extensive theory, however, references were not included, and in my opinion, the further insights were not the most interesting effects or requirements of this problem formulation, and I would like to discuss this more later on. And then they also cut off the graph at an unreasonable point, and when I asked the question, I don't believe that this was a reasonable justification for why they cut off the graph, and I will also bring this up in the discussion. So moving on to the insufficiently fulfilled points, we think that the parameters, which is overall, of course, the main, the main description of the task, was not investigated thoroughly, as they only varied 3, and most of the time was spent on this further insights analysis, which focused on frequency, phase portraits, which the task does not focus on. Furthermore, we think that the regime of self-inductance would have been nice to see, since the inductance is not relevant throughout the entire motion of the magnets, but in my opinion, rather only for certain conditions, such as low resistances. We also see that the eddy currents have not been modeled, which is a property of the magnet, and the magnet in the experiments were not in the coil, which the problem statement states that the magnet should be oscillating within the coil, which we thought was just a small thing of the problem statements. And then they also, for modeling the critical velocity, we think that they did assume a constant damping. However, I would like to discuss this further in the discussion. So now I would like to welcome the reporter to the discussion.
Go ahead, so the discussion time.
Okay, so first of all, I would like to discuss the experimental regime under the experimental regime which you investigate. So can you open a graph where you have the time, just the time, or for example, with time on the x-axis, any graph, right? Here, when I asked you in the previously why you cut it off at this time, you said that this would make the graph look more messy. However, in my opinion, I think that this was actually a correct thing to do, in my opinion. However,
Yeah, like,
okay,
I think you agree that, like,
this does look messy. However, I think it was correct that you cut it off at this point. However, I think it's for another reason, and this is because after the coil is pulsating with a magnet, after a certain amount of time, the oscillations will be very small. And as you presented in your positive explanation,
like the traffic up here.
okay, wait, yeah, what's it? Let me just finish my point. So, as you put in your positive explanation, the magnetic, change in magnetic flux will be just here and here, right? So here it will be very minimal, as you presented in your positive explanation. So, as the, of course, damping will happen, the oscillations will be smaller, and will occur along this region. So at this point, we think that the electrical effect will be very negligible, and the damping will mainly be governed by the mechanical effect. And the problem explicitly states that we should investigate electrical damping. So this is why I think that it was a good suggestion to cut off the axis here. However, I think that I disagree with your reason. Do you agree with this, or
Yeah, I agree. Like, yeah. So that's.
do you agree with the explanation?
It's mainly both like the ability for you to like see that the points of the experiment actually align in theory,
Yeah.
And also potentially like the damping. Yeah.
Yeah, so I think this is like also a reason for this. However, I think a more justifiable reason would be the fact that mechanical effects the mechanical effects dominate over the electrical effects. However, yeah, I think both of our reasons are valid here. So I would like to move on to the next point, which is the resistance of the coil. So I just want to briefly ask if you accounted for this when calculating the resistance. Because I just want to clarify this because I think it was clear.
Yeah, this is the resistance of coil.
Okay, thank you. So I think I agree that this is a nice point to include. And then for the inductance, you mentioned that you did include it in your theory. However, did you investigate which regime it's prevalent in?
So the inductance is over here, but if you just do a quick like order of magnitude calculation, then you can also find that like even if we neglect this, then like the effect on the final theory for this can be basically negligible.
Yeah.
However, we still include it because like it's part of the model.
Yeah, I agree with this point. However, I would like to see, or do you have any ideas, maybe qualitatively, on when the inductance would be dominant, or when it when it would be dominant?
So for example, like if the spring constant is extremely high, then like then it would be oscillating very quickly, and omega would increase, and so this term would like probably become more.
If the spring constant is very high.
Yeah, so that means like the frequency is high.
Like this spring constant. Wouldn't the damping occur like at a faster rate?
Well,
If the spring constant is greater?
no, like you asked whether or not you asked like in what kind of regime,
Yeah.
then the inductance would be more important. And the reason the inductance is not important is because of the angular frequency of oscillation is quite small with the spring constant of around 8 total, and 8 units per year total.
Yeah.
And so when we increase the spring constant, then the natural frequency will increase.
Yeah.
And when the natural frequency increases, then this derivative over here will increase, and so that will make this term more significant.
So if I understand correctly, you think that your opinion is that the inductance is governed mainly by the mechanical motion of mechanical motion rather than electrical effects? If I just understand like just briefly, yes or no?
Essentially.
Yeah, so I would like to disagree to this point, and I actually think that the inductance is mainly affected by the resistance, for example, the resistance in the coil, or perhaps an external resistance which the system is connected to. And just as a follow-up, did you actually connect an external resistance to the coil to the system? Because I think this was a little bit unclear in your experiment setup.
Yes, that's exactly how I varied the total resistance.
Yeah, okay, thank you. Just to clarify that. Yeah, I think, so would you agree with me that perhaps the inductance would also be affected by like electrical effects such as the resistance?
No, like the inductance of the coil is an independent factor. Like it doesn't, it may be correlated but not causally influenced by the coil.
Okay, how about if you change, for example, the coil windings? Do you think this would have effect? Since you do change the
It
coil
doesn't
windings.
causally affect the inductance, right?
However, we do change the properties or parameters of the coil itself, so would you not say this affects the inductance? Since previously just mentioned that the inductance is the inherent effect of the coil.
Yeah, so like as I said as well, in the simulation we do account for like every single term. We do not
Okay.
like problem solve.
Thank you. I think we can agree to disagree on this, and we disagree that the inductance, he thinks that the inductance is mainly governed by the mechanical terms, whereas I believe that it is mainly affected by the electrical. However, I would like to move on to the next point, which is the release mechanism which he used. So I think that the dual spring mechanism is a very nice and reasonable setup to make. However, you mentioned that you also had a release mechanism, which in my opinion is an unnecessary thing to include, since I think the dual spring mechanism is enough to ensure that the oscillations are mainly in the Z dimension.
I disagree. Because like, first of all, right, if you release it, for example, if you release it, for example, by hand, then perhaps you may like pull it sideways somewhat, and then this will cause some initial amount of radial oscillation, and that initial oscillation will cause the theory to disagree. Of course, you can truncate the initial part, but then like that's like not very in the spirit of showing the full theory.
Yeah, I agree with you that truncating the initial components are not like nice to model the full motion of the magnets. However, I think it is sufficient. I think it is sufficient enough to just have a simple hand release, since it is a dual spring mechanism, and I would suggest that maybe if the coil is here, then if you just align the magnet at some position here, then you can just simply release it and it'll start to oscillate.
Also, I'd like to discuss the air resistance term, because you mentioned.
Can we wait and first complete with this point, and then we can go on to that point if you would like to. However, do you agree that this method to simply release the magnet by hand is sufficient, since you do have a dual spring mechanism? So I think that this is enough to ensure that the oscillations are strictly in the Z dimension. Just a yes or no.
I disagree, and I think it's actually really necessary.
Okay, I think we disagree on this point. However, I would like to move on to the next point. So, similar, like connected to this. So, during your experiment, the magnet oscillates outside of the coil. Am I correct? All the way through. So coming back to the problem statement, I would just like to highlight that it does state that the magnet should be oscillating within the coil.
Yes, it does like go back into the coil.
However, it does go outside the coil as well.
But part of the problem is literally investigating how it affects the damping.
Yeah.
And one very important regime of the damping is when the damping is maximum, and that actually occurs when the equilibrium position of the magnet occurs at the end of the coil. And so we of course want to show this this case, which is like really important.
I think this is a nice way of showing it. However, I don't think that every parameter variation or every trial should have included this, especially since the problem statement does not state this. However, I see that we have come to a disagreement on this and on whether the magnet should be within the coil or not. Where I believe that this is an interesting phenomenon to investigate. However, it shouldn't be central, and all the trials shouldn't rely on the magnet oscillating outside of the coil. However, I would like to move on to the next point, which is your further insight slide, where you mainly focused on the frequency you plotted phase plots, which yes, I do think are very nice. However, I do believe that the parameters investigated were very minimal, since you only varied 3. And I think that since this is a major part of the problem statements, this should have been the major focus in your presentation. Whereas in my opinion, I think the major focus was more on the frequency peaks, which I believe is to be kind of irrelevant, but interesting in some way. What do you think? Do you think that the
I strongly disagree, because like actually we did like we varied 6 different independent variables. You can see like 6. So
sorry, I think
1, 2, 3, 4, 5, 6. Right, and so we actually varied 6 different independent variables.
Wait, could you show them again? Because I'm sorry, I think I missed.
Yeah, so 1,
Yeah.
2.
For axial offset, is that the initial release position? Just to clarify.
It is not the initial release. The initial release position is the equilibrium position of the magnet. So like when you're
So what's the difference between this and the release position? Just to clarify.
Yeah, so I was just about to explain that. So like when the spring is oscillating, then there's a position where like it is equal. Like if you don't have any oscillation, then it will just like stay at rest over here. And so we can adjust that equilibrium position to be at different points of the coil. And actually it's really important, even though like maybe it is also outside the coil, over here at the coil edge, that
Thank you. However, I did see that in terms of time with the focus, right? I think the explanation of why this occurs would be interesting, since we are to investigate the parameters and their effects that it has on this phenomenon, rather than the frequency or frequency.
Okay, time is over, so the 1 minute for the opponent summarizing the discussion.
So yeah, I would like to say thank you to the opponents for discussion. I think we clarified a lot of uncertain points. So firstly, we discussed the experimental regime, where he has graph off, we disagreed. I mean, we agreed in these points, however, due to opposing reasons, where I agreed that the graph should be cut off at this point. However, he stated that this was due to the fact that the graph will become messy if we do the full regime. However, I suggested that this may be due to the fact that the electrical effects dominate purely in the initial regime. Then we discussed inductance, where he suggested that it mainly depends on mechanical parameters. However, I disagreed and thought that it's more reliance on electrical things such as the resistance. Next, we discussed the release mechanism, where he used a dual release spring mechanism, which I thought was extremely sufficient. However, next he also mentioned that he has a release mechanism which I think is unnecessary. However, could be nice to include as well. And next, within a coil regime, which the problem states, I think it was nice to investigate the outside. However, this should have been done qualitatively and maybe briefly and not really.
Okay, the time is over.
Thank you for the.
Okay, that's the moment for the question from the reviewer. Go ahead, 3 minutes.
Okay, my first question to the reporter. Could you please explain where did you get the magnetic field equation for this specific magnet?
Oh, so you mean
How did
this
you derive it?
equation? This equation.
Yes.
Okay, so we basically derived it using the Hankel transform machinery that we established earlier, right? You just have to
Sorry,
integrate
louder.
the coil.
Louder.
So you just integrate the previous Hankel transform machinery.
Okay. My next question is, how did you arrive to the Bessel functions in the theory, and what role they play in the further records?
So the reason why we use Bessel functions, over here is because like the magnet has like cylindrical symmetry, and in this kind of case, then we would solve the Laplacian, like for example, this cube also explored it using the cylindrical coordinate system, and that also just happens to lend itself well to like Hankel transform based solutions.
Okay. My next question is about the phase portraits. Could you please explain why your phase portraits take the form of the looping curve and not of the not looped curve?
Yeah, so as I said, like the reason why it will form a loop is because like essentially like you will have these two state variables, but like there's also like a third state variable which is the velocity, and like when the mapping is not a bijection, which occurs like when this happens, but like the polarity of the velocity may be both positive and negative at the same time, and so that's why there'll be this low in 3 dimensions when you add like the velocity as the z-axis, then like of course there will be no crossing.
Right, but question to the opponent, do you see any issue in the explanation of the reporter and in the phase portrait itself?
No, I mean, wait, was this theoretical investigator or experimental?
Theoretical.
Yeah, both.
I think.
Yeah, it's correct.
Yeah, I mean, his theoretical model seemed correct to me, so I think if this was the results he obtained from that, it should be correct. Yes.
Okay. So my next question to the reporter: did you find all parameters experimentally for your first model?
Yes.
Okay. Okay. So thank you very much for your answering.
Okay, time for preparation.
I was like so scared I wasn't
Okay, time is over, so go ahead with the talk.
Hello, my name is Anna, and today I'm reviewing the task number 2, electrical ducting. So, what are the advantages of the reporter? First of all, they provided a qualitative explanation. They divided the process into 2 phases and described the process well. Then, for the experimental setup, they used hands to release, made the installation to achieve this symmetric motion, and provided generally good and solid experimental setup. For the circuit modeling, they first of all implemented the Kirchhoff's law. Then they found the magnetic field for their specific magnet, which is actually really good because this formula is not really classical and shows a deep physical insight. For the number of coils, they found them experimentally. They compared them with a theoretical curve, found inconsistency, and implemented a new theory, and merged them with a scientific impact. Then, for the Fourier frequency analysis, they demonstrated a heat map, and then they validated the odd and even frequencies relation. Finally, they analyzed the phase portraits, which is a good additional aspect of the report. What are the disadvantages? For the qualitative explanation, they did not clearly explain why and how does the process happen. They only described the process and used computational analysis. So we would suggest to expand the qualitative explanation a little bit more. For the second part of the report, they only qualitatively explained the phase portraits, did not really make a model which would predict, they did not really experimentally analyze the second part. So then they analyzed, they were not clear conclusion for the statement of the problem, how it links to the statement of the problem. Then they were one incorrect answer. So they said that the part with the derivative of the current would increase when the spring will speed up. However, we believe that the part with the acceleration would actually increase, so it was kind of messy. So for the opponent, for the disadvantages, they questioned their assumptions. Their theory, they asked about the temperature and found the missed parameters. This was a solid part. They scrutinized various aspects of the presentation, including the hand release. Experimentally, they asked theoretical questions. Next, they found the problem that the second part with the phase portraits does not really link to the problem statement. For the disadvantages, they completely disregarded the part with the phase portraits, while it could actually be investigated a little bit more. They missed several questions on phase portraits and the fact that this actually kind of incorrect shape. So on to the discussion. They first of all started that at small amplitude the oscillation damping is mainly mechanical, and the reporter actually agreed with that. And we think that this is basically correct. On to the next statement, the opponent stated that the inductance is dependent on the resistance. While the reporter actually disagreed and said that the inductance depends on the spring constant. This debate is kind of disconnected with the actual problem inside. But we would say that we agree with the opponent and that the inductance actually depends on the resistance. Next on. When we asked the question to the opponent about the phase portraits, we believe that she gave an incorrect answer, as if we account for the friction in the model, the phase portrait actually would not loop and look like a spiral. Okay, so thank you for your attention.
Thank you so much. There's the floor for the closing remarks of the report. Go ahead.
Okay, so firstly, I think there's like some confusion about exactly what meant by inductance. Like I never made the claim that the actual underlying inductance depends on anything mechanical. Rather, like the way I interpreted the question was like whether or not the at what time, like in which regime does the inductance actually affect the electrical damping? And you can see some calculation over here in the appendix of and you can see like it depends on the frequency, which depends on the spring constant. And you can read this. Furthermore, for the graphs, we believe that the current time frame is correct because you can see the EMF and the force at the correct scale, and you can also see the theoretical points. And furthermore, for the experimental setup, we believe that the hand release the hand release mechanism is not a good idea, and the dual spring setup plus the axial release is like a good addition, regardless of whether or not hand release is already sufficient. And also, furthermore, I think we actually completed the problem pretty well because we analyzed both the axial offset and the radial offset, verified and checked it with the theory, and also showed that and analyzed the harmonics and the dap motion, and showed that it has good theory experiment alignment. And we also tested 6 different parameters, which are the resistance, the axial offset, the radial offset, the number of turns, the number of magnets, also the strength, and also like and also the initial amplitude. And so actually, I believe that the task would be classified as complete rather than incomplete, as she has claimed. Yeah, so those would be my concluding remarks.
Okay, thank you so much. So we arrived to the jury questions, so I open that part. We have 5 minutes. So Frank is first.
How did you implement your numerical solution to your final model?
So the final model is just like the numerical simulation, which is based on the differential equations that we had previously. Like if you want to take another look at the differential equations, like we just solved it numerically.
But more detail. What numerical method?
So for the integral, like we just used some existing Python libraries to quantitate the method function integrals. Like this is a very well-known form of method function integrals, and so like we can just quantitate like that. And for solving the couple differential equations, then we just use like IYPT2026 and implement it programmatically. And yeah, we use pretty small time steps and verify convergence of the differential equation solver as well.
Thank you.
Okay. Who next? Go ahead.
What is Z and S here?
Z, maybe a top by through a diagram. So, like, if we have a magnet over here, then Z over here, we define as like the vertical position, and S as like the radial position.
Oh, okay.
So this would be S and this would be Z.
Also, where are the phase portraits corresponding to the solution of those equations?
Yes. Of course, like we set the error resistance to K to 0. For like as I mentioned, like it would only stop
But
in
the-
resistance to 0 for
But the other resistance was present, right? Like the damping from the coil in those phase portraits, even though there was no damping in the first portrait.
Yeah.
Okay.
Okay, so go ahead.
Can you go to slide 23, please? Is this the dots? Is this the plot from your experiment, or
Yes.
is it? Yeah. Is all experiments in one plot, or is it just one run?
This is just one round. I'm just demonstrating over here how exactly we quantify that amplitude. By the way, like we also apply like a small correction because like this is like a finite window size for the smoothing. But like yeah, like it's in the appendix.
Okay, here we have another one.
Right. So you talked in the discussion about setting the initial condition by hand and then releasing it, and you claimed that it matters what the radial component of the a magnet is. But if we go to your final model, so the equations for Z and S are decoupled. The one depends exclusively on Z, and the other depends on S. So that implies that the effects do not affect each other. So then my question is, what is the physical reason for why, you know, controlling the radial component of initial condition matters?
It's not exactly decoupled like you see over here.
Oh, I see. So, okay, let me just check that. So you've got Kirchhoff's laws. Okay, I'll have to think about it, but thank you.
Okay, so, William?
So for the opponent, one of your biggest points of disagreement was you interpreted what the reporter said is that the spring constant changes the inductance of the coil. The reporter in his concluding remarks said that no, the spring constant doesn't affect the inductance, it affects that derivative, the IDT. Right? That's basically what he's saying. And he said because that number gets bigger, then maybe that whole term then becomes relevant. Do you agree with his suggestion that
yeah, the term becomes bigger. However, there's also ways to make the inductance of the coil, like that specific variable, larger as well. So I think that while it does make the term bigger, there's other ways to vary the self-inductance of the coil itself. And also, one correction I'll make is that when he mentioned the spring constants, he said that a greater spring constants will lead to like a larger term, like the differential term. However, I disagree. I think it would be the opposite effect. A greater spring constant.
Okay, so it looks like we are done with the question round, so we need some time for